We have this idea that making your step size h in Euler's method smaller will give you a better approximation for a solution. But how exactly does h affect the approximate solution that you get from Euler's method? And also, if you want to find an approximate solution, how do you choose an appropriate step size? Let's look at an example to get a feel for these questions. And we're going to use the differential equation dy dx equals 2xy. For this particular differential equation, of course, in practice, if you needed to solve this, this is separable, so you wouldn't want to actually solve it using Euler's method. You'd solve it exactly. But the point of using an equation that we can solve exactly is that we'll be able to look at several different values for h and see how the approximate solution for those various step sizes compare to the exact solution, which we can find because it's a separable equation. So here's our example. So the point A is our initial value for Euler's method, and the purple curve is the exact solution that goes through that initial condition. We have our step size showing up here. Right now it's set to 1. And we have this idea that large step sizes should give you bad approximate solutions and smaller step sizes should give you better approximate solutions. You can see if your step size is big enough, the approximate solution you get from Euler's method is actually pretty terrible. In this particular example, if we drew the slope field here, you can see there's kind of a dividing line along the x-axis. Solutions that are above the x-axis go up, and solutions that are below the x-axis go down. And by having our step size be so long, we jump across this important dividing line, and so our solution diverges very strongly from the actual solution. But a step size of 1 is pretty big, so let's make it something a little more sensible. How about a half? Okay, for this step size, a half, just kind of by coincidence, we land exactly on the x-axis, and that kind of zeroes out our approximate solution from then on. If we make our step size a little bit smaller, then we aren't jumping down into this region where the solutions look very different. Instead, we're staying in the upper half plane, and so now the approximate solution generated by Euler's method looks sort of like the exact solution. But still, in the grand scheme of things, the step size of 0.4 is pretty big. And so we can make this step size smaller, 0.3. And you can see as we decrease the step size, the approximate solution is getting closer and closer to the exact solution. And that's pretty much what we expected, so it's good to see it happen in practice. Make the step size even smaller, you get a better solution, and smaller, you get a better approximate solution. Okay, but there's a cost to decreasing the step size like this. There are two things that are happening as we decrease the step size. One is the approximate solution gets better, but the other thing that happens is the approximate solution has a lot more points, right? Remember, you have to do one round of Euler's method for every step. So to get from -1 to +1, with your step size being so small, on the order of a few hundredths, you have to take many, many steps to get from -1 to 1, and that's why there are so many blue dots along this. Right? If we decrease the step size even more, you get a lot more dots. So many, in fact, that they all kind of blend together. So there's this trade-off when you are working with Euler's method. You'd like a small step size because a smaller step size gives you a more accurate approximation, but you would also like a large step size because larger step sizes means less work. You just have to generate fewer points. Usually the best step size to choose is going to be somewhere in the middle between large and big, so that you don't have to generate too many points, but you at least get decent accuracy. What in the middle means, or what small and big step sizes are, really depends on the particular application you're working on. And so you'll have to understand your situation better before you have some idea of what kind of accuracy you need and what sort of computing resources you have available to you to grind through all the many iterations of Euler's method. One nice thing about Euler's method is since it's just the same formula over and over again, you can program a computer to do it pretty easily, and a computer can do a million iterations of Euler's method in the blink of an eye. So a computer is a really strong tool to generate approximate solutions for differential equations, just because you can choose a step size that's very, very small and still get an approximate solution in a reasonable amount of time.